Welcome, everyone. Welcome to the Ubuntu Summit. I'm glad to be here. This is the second time that I am here. Last time no presentation, but this time I brought something. I'm talking about this specific thing today and how exactly we made it in terms of technical decisions, the software that runs inside it, and these kind of things. A quick first introduction. So my name is Filipe Coelho, known online as FaltX. I work on this tech stack not for the MOD Dwarf, because the company made some other products before. So I've been working on the field for around 8 years, not continuous, but around 8 years in total. I do other Linux audio related things. So some people from here know me from that. Today, to show in the summit, I decided to just present something about the Linux embedded real-time audio side of things. Yeah, that's basically it. So first, what is this little thing exactly? So this is basically what you can say, like you can call it an effects pedal. It runs a Linux system inside. There's some, I guess you don't see it from there, but it has some I/O on the back for receiving MIDI, receiving audio, receiving other things, sending to the speakers. And I can just demonstrate it to you directly. So to be clear, this, you power it on, there's a Linux system inside. It exposes itself, you connect it via USB cable, so like one of those printer cables. You connect it to the PC, and the device presents itself as a USB gadget, in this case specifically a USB network gadget. If we go to the browser, because now I have to actually look at the screen. So because it's a network device, there's a DNS server running inside the device, which can tell the machine that is connected to it what is the IP that it should use automatically. Which on all the mod units, this is the MOD Dwarf, but you just go with a 192.168.51.1 if the thing is connected to your laptop or your PC or whatever, and it loads a web server. So I could even use here moddwarf.local because there's some MDNS stuff figured out in here. This is what you see as a representation of the things that run inside the device. So basically, on the bottom area, you have plugins, stuff like pedals, kind of. Goes from left to right. You have some cables. You can move stuff around. You can control parameters if it was like a real pedal. You drag and drop stuff to add more stuff to your pedal board. There's configurations, there's connections to MIDI things, all this sort of stuff. And you can assign stuff, for example. I don't need to demonstrate it, just to say, I can assign this knob to a device-specific control, I assign it to knob 1, and every time I rotate knob 1, it does something on the plugin side. Then you have your collections of what we call pedal boards, which are projects. They are saved within the device, and they just click on one, you load it. That's basically what the device like. This is a visual representation of what the device is doing. The device is not actually rendering the graphics. The web browser is, because it exposed a web server. Basically, the only thing that it does is tells the device what to do, basically. But that is just to get a quick introduction to more or less try to explain what the device is doing. There's a lot of stuff on top, which I don't want to get too much deep into it because that would be too much to cover. But just to give you like a little introduction of what the thing can do. Basically, each of those pedal little things, these are plugins, but exposed as a pedal kind of thing. So then you combine them, you connect them, all these other things you have in an audio setup. Yeah, and I want to talk basically how we how we engineer the entire thing from start to finish. First, to define the targets that the company and the tech engineers wanted to do. So we want to have something that is fully capable, that is something that you take on stage, they can rely on it, not something that is, I don't know, breaks easily, something that is robust enough to be sold as a commercial product, basically, because it is sold as a commercial product. It needs to do audio processing, so it needs to be low latency. We also have MIDI because, in general, it's useful. It's not too hard to implement. People appreciate it. We used to do other devices that were more focused on the MIDI. This one, the Dwarf in specific, is more focused on the guitar side of things. But yeah, the goal also is to make it very easy in use. In order to be a viable thing commercially, it needs to cater to all the users that they are non-techies, stuff that they don't want to compile anything, they don't want to build anything or build the plugins. So basically, you get the device, everything is like clicks and clicks. There's not, even sometimes clicks are a bit troublesome. So make it as easy as possible, including the updates, so you don't have to run anything, install anything on PC. As you saw, the thing runs on the browser, so there's no application that the user needs to install in order to just load the thing and set up the unit. The same is kind of true for the factory reset, where you do have to install something special, but I'll demonstrate it. A little bit later. But anyway, hopefully that is clear. Just to have something reliable, something that is good enough, low latency is the focus. So the first things that we need to decide. Obviously, we want to be the smallest possible form factor. So you cannot go with the ATX board, for example. Even the mini or Mac or I don't know what is the smallest anyway. Those don't work very well. So like on x86, typically you don't have things that are so small to fit in inside a case like this. So usually the solution is to go for an ARM device, an ARM board. There's potentially the idea of using something like a Raspberry Pi or something that already has everything. But from the experience that we had with some testing, there's a lot of caveats. I don't know. There's some issues that is hard to work around, and it provides support for some of the things that is not needed. We have to consider price as well, because this needs to be scalable. We saw recently, for example, Raspberry Pi was out of stock, which becomes a problem if you rely on it to build something else. It needs to be able to also be sold for the long term. On the Dwarf in specific, I'll mention a bit more later, but the board that we tried to go for, it was promised to us to give 10 years of support for this hardware. So we ended up doing a very custom board for the unit, where if I show it here, the thing you see on the right side is what we call a core board, or a SOM, basically. It has CPU, it has RAM, it has flash memory, a bunch of other stuff, and it's all in a single, kind of like a RAM stick. Size-wise, because it's hard to see from there, I would say it's on the same size as this screen, just a bit taller vertically. So it's very tiny, and it contains everything. We even it even has graphics. It has a GPU inside, which we don't use because it's an embedded system. But yeah, that's the recommendation, and typically what we go for. We just go for one of these tiny little boards. So idea then is to experiment with a bunch of boards just before making your entire selection. I'm putting like a little exclamation point in there, because just to emphasize a few things there, to give out some lessons, because On this one in specific, this is called the PX30. We picked it because the vendor promised to us that they were going to support it for 10 years. So like in 10 years, if we want to buy some more, we can. Like we're not producing it ourselves, so we cannot manufacture these. We have to rely on them. And they broke the promise. So they already stopped support for them. The issue was like Firefly promised this based on some promises from the actual CPU, the ones that made the CPU, and the CPU is not being made anymore because of like lack of interest. So this thing, it's like the Dwarf at some point needs to change to some other model by force. We have enough in stock for quite a few units, but then we know it's going to stop. Then we have to move on with something else, which is tricky. There's also the case of researching the boards properly in terms of support to make sure everything is working properly. On the PX30, because of the 10 years, we kind of just assume we have enough time to do everything. But then we don't. Now we have to kind of shuffle things around and try to support something new very soon, which sucks. The entire point was to get better support for this over the years. Then we have experience, but then we cannot rely on it anymore. The things that we use on this are the I2S. So it provides some audio. It doesn't do the audio directly, but it provides the interfaces to do the audio, which is called I2S for this. It has the UART for the serial lines, USB. It needs to support both USB host and USB gadget, because we want to have like MIDI controllers like these. These use USB host, which means the device itself is the gadget and it connects to the unit via the normal USB-A port. Then the unit itself also provides USB, but USB gadget, so the unit connects to other things. And not all boards actually support this. Some years ago, even the x86, there was no boards at all that even come with this. But yeah, it needs to support all these things, and this board did. So we picked that one. So to begin, what we usually first do is to get a dev board. They're actually from the manufacturer. In this case, it was Firefly. I put a picture in there. So that little SOM, the core board, fits into something else that provides all the I/O, provides USB, provides even Wi-Fi, Bluetooth. You need to connect some radio things in there, but it provides everything. Even provides HDMI output and LVDS for screens and other things. We mostly don't need all of those, but this is very handy for the initial development. You do need to get one of these. So basically what we do is to go directly to the vendor, get their so-called BSP, so a developer package that contains a runnable system. So you read that documentation, you deploy it on your device, then you can get a rough, you get to know how the device works, basically, if it works good or not. It should be able to do some testing at this point, even get a bunch of different ones. And the testing, typically I would recommend from personal experience to check if the mainline support is there. On the graphics, I wouldn't count on the graphics being supported in mainline usually. That's typically not the case. It's very peculiar how all the graphics on these boards work. But if you don't need graphics, which is the case for the unit, then all the things that are a lot simpler, they mostly just work. So if you can run on mainline, check if the CPU, if the board runs on mainline, and try to go with these. Because if you have something that is static that does not connect to anything, it doesn't matter. But this, for example, on a kernel update, we can enable now exFAT and NTFS if we want for USB sticks, which if we're stuck with the vendor kernel, we can't. So another thing, now comes the MIDI 2, for example, that is coming to the Linux kernel. and we basically get it for free if we are already on mainline. The thing to test as well is to also check the real-time priority. Hopefully now, if the vendor already provides a kernel that is recent enough, you can use the preempt equals full, which basically mimics a real-time kernel. Actually thankful for that, because in the years before it was a pain. If it's slightly old, you can still use like the voluntary preempt and the threaded IRQ, which kind of gets you alpha there. The thing is to test the real-time audio. Like, try to get the system, even if you're not building anything yourself. Just get the stuff from the vendor, see if the performance is good enough, see if if there's any oddities. Sometimes some hardware is not capable of, has some weird things on RAM or... Anyway, it's good to actually be assured that the thing works proper. On this unit, I wished I was involved more picking the CPU, because it turns out the USB driver for this is quite bad. So there's a lot of user reports and support cases where just the USB driver just stops. And because it relies so much on USB, the device stops. I mean, you can still use it with the controls and the knobs and these things, but yeah, becomes tough. After you do all this testing, hopefully with more than just one, then you finally pick a board, and what you do is that you start to design an actual custom board around it. So instead of using the dev board, now you have a whole thing that you design yourself. I was not involved in that at all, so I'm not a hardware engineer, so I don't actually know how that's supposed to go. And I know that someone is going to ask this if you don't know about these boards already. These sticks, they're not compatible with each other. They're not proprietary, because, I mean, kind of. It depends on your definition of proprietary, but they're not interchangeable. So if you make these, we call this on the MOD Dwarf, we call this the bottom board, because there's another one that deals with the controls and everything. You can see some little pins on the top left. This connects to the other board, just to provide some separation and to just make it easy to assemble as well. Because then you can just open it's two different boards. But yeah, basically you cannot just get a new SOM, a new core board, plug it in there, and more power. No, so much stuff involved. The mod company actually did it for the Duo. For one that is kind of similar, we changed the manufacturer, but the CPU was still the same. And it was so ugly, because the way that we did it is that we matched the lines from the first board to the lines of the other one. So we have an adapter that plugs in there, and then this board plugs into the adapter. Very finicky, but it ended up giving support for the unit a little bit more, because the other one also stopped manufacturing, so we had to adapt. But yeah, not interchangeable. Then after you have this, supposedly you have a hardware engineer that does the design, prototyping. You start building. But actually, before that, you cannot just start building yet. You need to define exactly what to build. There's idea, even within mods, we had initially the idea of just using a normal distribution, Linux distribution for this, because you have a lot of stuff already ready to go. But we're faced with some serious issues, as in the versioning problem. I was even maybe trying to put in the separate slide, but I hope here is understandable, where if you have stuff that updates all the time, you want to have the unit in the state that if someone reports an issue, you want to be able to have that same exact version of everything, so that you can reproduce the issue. What happens on typical Linux distributions is that there are updates all the time. Maybe like a libc update or some patch for some other library, random thing. They broke things. then you don't get the bug anymore or some package updates introduce the bug. It gets very tough. So we just decided to not go with the already made thing. We make our own. Also, there was the case of device-specific optimizations, where if you pick a Linux distribution, the normal one, they're going to not optimize for your device in specific, but for something generic. So it runs on the most, like, all the available systems possible, which actually we don't want. This is like a very specific single board that is always going to be the same. It's the same case, I don't know, as a game console or some other devices that are always the same CPU, always the same hardware. So when building, we want to build the entire thing optimized for this specific CPU. And I mean, general distributions are not going to do that. We also want reproducible builds, like the same idea of the versioning problem, but in a way that if 2 years from now, we need to come back to an older version because it was working correctly, the new version is not anymore, we want to be able to just exactly match that build that we have before so we can tweak it more. If you use, I don't know, distros, how do you get to an older version on a specific set of libraries? I don't know, it's a bit tricky unless you catch everything, but yeah. There's also the case of updates. What I mean by this is to have the user be in control of the updates, but still don't break the system, which is tricky. So we want the user to still be able to, like, we release new stuff, we make new stuff, everything goes together to just update the software. It's the same case as the factory reset in case the user wants to reset everything. We need to make a package that contains the entire OS. So with this, on the mod platform, because we made the initial design for the tooling, on 2016, we decided on using Buildroot. The main idea was just, it creates a single image, the rootfs. We run it inside the container because we had some issues of, depending on the host machine, some things behave differently because different compilers, different flags by default. There's a whole mess. Sometimes I don't know, the compilers change, the build breaks, and it builds in your machine, not in the other developer's machine. We ended up just, the entire build for the platform runs in the same container always. So it's completely reproducible, kinda, because the container can change a little bit, because I mean, it's like based on old Ubuntu. So there could be updates to that, but the actual thing it generates is typically ends up being the same. And we added a lot of stuff on that, on top of the build root. I mentioned build root here because this is going to be crucial, but nowadays build root is not so popular anymore. It was back then. Now Yocto seems to be the most popular choice. Somebody that builds the kernel, it builds whatever packages, and then outputs like a single image at the end with the entire rootfs. It can be like a squashfs image or a tar image or ext4 image or something like this. I'll demonstrate quickly exactly what I mean with this. We have some of the tools here on the repository. And it's a bit awkward for me to write like this, but okay. Just for the people not familiar with Buildroot. So with Buildroot, you define what is your target. So in this case, we have ARM64, it's a Cortex A35. It builds for that. We use external toolchain, in this case, cross toolchain ng. We just define whatever that thing is installed, but you can use anything. It already provides, even if you want the thing to be downloaded, install it by Buildroot directly. We use something else because then we can update the toolchain if needed, without needing to update Buildroot. Basically, this provides the typical thing you might be used to. You define your kernel if it's needed. I'm showing off the thing from the plugin builder that we have, so it does have the kernel. But basically, to give an example, we need to install something new that is not there yet. Let me pick something more useful. We go here, we pick, I don't know, this one. We'll let it save. This like build root by itself is not this. There's a couple of more things involved, but we build a couple of tools on top of build root just to, instead of typing manual make commands, we type just something a little bit more simple. But this is not too complicated. Thing is, after this, what you get is basically it changes the configuration that you already have. Like it spits a configuration for you. After you make all the choices, it builds this, puts it in there. Actually, give me a second. So I'm basically now, I mean, you don't see exactly the main commands because I'm hiding those away behind shell scripts, but assuming this goes fast enough, it's going to just build the thing and the dependencies as well. I'm not doing anything special. I just picked one thing and it's building everything for me. So there's a couple of dependencies of the new package that I selected. That was a very random one. And the thing is just there. There are cases where, of course, the stuff you need to package, if it's like the stuff you made yourself, it's not going to be there directly. So on this case, you create your own package. I'm going to give an example of such a package. Let's see the custom jack package that we have, which basically, hopefully that is readable, but this is a makefile. Build root is all about makefiles, but you define the version, where to get the source from. You can pick the license if it's if you need that sort of thing. Then you define the build steps. This one is custom because it uses WAF, but if you have something that is more standard, you don't even need to do anything. You just say like where to get the source from is an auto tools package, and it knows what to do. And on the little here, the build is finished. So at this point, you would have a new image to do something with that already contains the new application that you selected. So then you can do something. That is the next step, actually, or one of the next steps. But basically, yeah. The disclaimer, I was kind of, do not forget, the tools that we created at MOD to build the entire thing itself, they're not open source, just to put the disclaimer there. The thing that I showed, the plugin builder, it is open source. So we have a way to build the audio plugins, the like little pedals that you saw there, and to build also the kernel if you want to modify the kernel a little bit. That is all open, all available if you want to do. The build system is more like a business reason than a technical reason, because then someone else can just copy the thing. It's still useful to just to explain how these steps are done. If someone was going to do something from scratch today, probably they're going to use the Octo because it became more popular. But yeah, just the little disclaimer there. So, okay, we have the thing going on with build root. Now comes the actual getting the hands dirty. So we need to go from the manufacturer, basically, the one that makes the board, and really understand how the deploy procedure works, because we're going to need to rely on it. Not just the deploy, but also how the boot situation works, because we probably need to modify the bootloader a little bit to work for our case. Initially, it's fine if we just build things manually, just put it in there. The intention is get the things to build with and run with something that is yours, something that the manufacturer did not provide, something that we built from scratch and can start modifying. If it's all manual, doesn't matter. On the case for the Dwarf, the tools needed is something called RK Develop, something that Rockchip provides, because the the unit, the CPU, for all the Rockchip devices that I'm aware of, there's a special mode called mask run, which puts the CPU in a state where it just listens for requests, and you can do raw operations. You can send an operation to the CPU via USB to just say, write this data to disk, do some testing, check the RAM, whatever things. And that is how the deploy mode begins. You can force the CPU to enter in this mode, and then you just send the data to the CPU to write stuff on disk, and then that's how you start deploying and booting the thing. So basically, get something that you build yourself, deploy it on the machine, and see that the machine actually boots. You want like a UART debug cable, of course, because it's not going to boot and do anything useful. So you want some debug information out of it. Like before proceeding, we need to make sure the device boots. Then we continue. First things to do is to, we have a kernel going. We add BusyBox to have just some small utilities. And a way to start the development proper, because at this point, it's just putting the things and flashing manually. We want to set up a DNS server, SSH server, and to set up the network gadget as well. This is not too complicated. Like the DNS server, on the case of the Dwarf, is DNS mask D. You just have to set up some basic options. You can even try it on your own machine before putting on the device. The G-Ether kernel module is just something that you enable as a module. You mod prop the thing, and it does the USB network thing for you. We have systemd on the Dwarf. Very happy for that, actually. And the idea is we have a way to push for things very quickly. So at this point, we should have a kernel booting, the system booting. It doesn't do anything. But we have a way to modify the kernel. And with this, we can start testing the hardware. So before now, we just assumed that the hardware works. It was not even booting at this point. So this now happens in parallel with prototyping a bunch of boards, see if there's any defects, and all this kind of stuff. One thing that I can do here as a demonstration to this, and the thing is, I don't know if I have it. Probably I'll skip it, but the idea is, because I already had built it before, we have scripted ways of building the kernel. I'm doing it live. Yeah, this is the kernel. Yeah, it's deploying the kernel to the device over SSH. And one thing I forgot to mention, actually, the device, because it provides a network interface, I can SSH to it. There's no restrictions on it. And I'm going to reboot the device. There's a little introduction when you SSH just to make it fancy. Assuming this works, we just build the kernel and we just push the kernel to the device, and the device is booting the new kernel. And that took no effort at all. You would just modify the kernel, whatever is needed, do one command, boot it up again, and assuming it actually boots up again, maybe have to wait a little bit. But anyway, because I'm not sure exactly what its time is, I don't have the full screen on my side. So assume it works. We push the kernel, we reboot. The idea is quick iterations, get it as fast as possible. Yeah, just don't reflash the whole thing one at a time. Anyway, Then we have partitioning, because we have a file system, yes. If things are booting up, yes. But we need a way, for example, to enter some kind of recovery mode. Also to split user data into system data, so that on the Dwarf is not so much of an issue, but on the first unit that Mod made, we had an issue with data corruption sometimes because of the bad NAND histories from quite a while ago. So we wanted to have the system be separate. Also because then we can update the system, but leave the user data alone. What on the mod side, we ended up deciding is just to have a restore partition, have a system partition, and have a data partition, which is, I mean, one of the choices. One of the things that we did is to create a kernel variant only for the restore mode, where the restore mode contains the entire thing. It contains the USB driver, it contains the tools to deal with the recovery, so that when you enter recovery mode, the entire kernel is rolling into RAM, and you can even delete the entire disk, and it still keeps working because it's running on RAM, unless you unplug it, and then, yeah. We have the warning saying that if you're doing the updates, don't unplug the device, because, yeah. But then on this special kernel can also disable a bunch of stuff we don't need to make it smaller. But yeah, just to keep going, because I think I'm actually a bit delayed on time. The thing that we need to do next then is to define what constitutes an OS image, because we want to be able to update the device. We have the restore, the system, user data is special. We already saw that build root creates a tar for us. So what we ended up deciding, this is for the mod case, is to have one tar that provides the system, the data, exactly as build root outputs it, and then some little metadata on top of it, which I can quickly demonstrate here. This one. So that little thing you see there, this is what we call a MOD Dwarf firmware, kind of. It's around 90 megabytes in size, but it contains just the sums of the files included, and then it contains some information about the device, especially also to say which platform this is meant for in case the users rename the file or something. This is a way for that the restore mode reads this file, reads this property, and kind of knows what to do. This would be something that I also recommend doing. And basically with this, let's go back. Yeah, we have a deployable device where we can deploy it, we create a tar, we put the unit in restore mode, and we have the restore mode just, what it actually does is to format the actual partition, the restore and the system partition, get that tar that build root generated, and just extract on top of it. So every single time is actually formatting the partition and extracting the contents. That is one way to kind of make it immutable, as in, it's the whole system. It's not the individual packages, the whole system goes in one go. And we tag it as like 1.1, 1.2, 1.3. The entire thing is the image, is the firmware. Something that we had to do lately on the Dwarf's lifecycle is to provide directly to the manufacturer, to the vendor, a special image. What I mean by this is to already have the manufacturer ship us with these core boards that come with the mod software inside. This typically involves some custom formats. They don't use the RK develop tool that is open source. They use something else. But it actually speeds up a lot of things, especially because we made the USB, the restore modes also have USB support, where if you put a USB stick in there that has the firmware, put the unit in the restore mode, and it just updates. Don't even need to do anything. So with this, basically on the factory, the system that we had was get a bunch of units that are ready, like already have the they are assembled, put a bunch of USB sticks in each one, power them on, wait a couple of minutes, and they're all deployed in parallel, and it goes very fast. Okay, now for the juicy stuff. After we get all this, then we go into actually what the device is supposed to do, which is the audio. So for these units, there's Jack running in there. It runs on top of the I2S device. The I2S device actually, like I2S from the CPU communicates with a custom, like a little codec chip, the Cirrus Logic, and then that drives the actual analog audio. This, like the DEC, basically, that's the Cirrus Logic thing. We have the mod software that does the plugin hosting and the web server, which is like mod host is the plugin host. Mod UI is the name for the web server that does the things that I showed on screen, and everything on top of systemd. So that, the boot is parallelized. If one thing crashes, it restarts again. Everything like working as intended. There's some extra steps made to ensure like these things are proper. So we have everything that is audio related running as a Jack internal client. So everything is in process. There's no external clients in there. For those that don't know, like Jack is an audio server. You can it provides a way for external applications to talk with each other via some IPC that runs on shared memory. If you have separate applications running, there's going to be context switches between like some applications sending buffers there and some other application is waiting on that. So for mod, we just basically run the entire thing as one inside Jack, basically. It's in process. That also means if the plugins do something bad, Jack also goes away. There's a special thing that got added to Jack a couple of years ago to just specify a configuration file, and then just loads everything in one go, assuming the unit booted properly. I might need to reboot it, but I can show you some other way. Anyway, there's a little file in there that specifies which things to load, and then it just loads everything. Only when it loads all the clients, then it notifies via systemd that Jack is running. So everything else that runs separately, in this case, only mod UI to the web server. Only then actually mod UI is allowed to start, because all the other things are good. Like we don't need those hacks of Jack waits that periodically checks if Jack is running or not. Like we want the unit to boot fast. So as soon as the thing is ready, notifies, and then mod UI starts right away. I have a note there that this allows for crash recovery because different processes. But I do have an issue here connecting, which typically means, yeah, I just have to connect this. Yes. Yeah, the machine does not connect to this automatically. Anyway, I'm going to demonstrate it very quickly. We have a little payload board running. Its processing is doing audio. I can even demonstrate that it's actually running audio by putting something in here. There's no connection to the speaker, so you're not going to be able to listen to it. But I can get anything that generates sound. This one. It's called the CEO because it's always calling for profit. So it just says profit, profit, profit. That's the CEO. Anyway, there's a little thing that provides a spectrum analyzer. So it's sending signal to that. The signal is running. I'm going to SSH into the unit. The password is mod, by the way. It's just. So I'm going to do kill Jack. Wait, is it refusing to kill? Let's really kill it. Okay. So Jack is killed. The audio crashed. But because systemd is running inside the unit, you just restart things. You click reload, and the thing is back again. And because the state is handled on the UI side, not on the host side. The host like just only does what it's told to do. Things keeps running, which is cool. Anyway, yeah, one extra thing is that also mod host runs registers one client per plugin, which means because Jack 2 has parallelized connections, basically you get parallelized audio paths because Jack already does it. So we get multiprocessing for free, which is cool. Anyway, after we have audio running mostly, then we need to develop all the custom tools. And this is something that you might not think that is needed, but it is, because it's very niche. So one that we did is the MIDI merger, basically something that just gets a bunch of MIDI streams merged into one, so that when you plug a MIDI device, you don't have to manually connect things. Everything is running on top of Jack. We don't want to also connect to each individual port. There's a way to do it that just gets all the clients. I'm going to show in the next slide. We did a peak meter, which basically every time there's signal, we send stuff to the top port. Basically, just a I2C bus. It gets some peaks, sends it on some other thread to the I2C. Then we get some peak metering. We did the SPA to Jack just to get some CV ports. It does not matter for this because there's no CV connection. There was the TTI MIDI, which is to do serial MIDI, but with Jack instead, because the default project only does ALSA. And there was a lot of fixing needed for that project. I'm trying to do, is a work in progress to do like an ALSA to Jack kind of thing, similar to other projects that exist, just to get the unit itself working as a USB audio interface, which is not going that well. It works well on Linux and macOS. It works terribly on Windows because the timing of the USB packets that Windows sends is completely... I couldn't find a way to get it to work properly. But because this is something for the users, which mostly are on Windows, we cannot ship something that only works on Linux and macOS. Anyway, we also then did a lot of plugins for this, the LB2 plugins. I'm moving on just to make sure we have enough time. The thing that I'm showing here is the audio graph that runs on the unit. Like the black little thing you see there, that's a representation. That's the actual connections on the unit. What this is what is called the pedalboard view, and there's a bunch of stuff happening behind the scenes that you just don't see. Like this connection is kind of easy to follow. We have this connecting to this is the Mod C adapter. This is an old screenshot, so it doesn't apply exactly to now, but the peak meters are connecting directly to the system capture one, which means the input peak meters. Then we have the output peak meters going to a monitor client just to be able to push everything into this client if we would need to do some post-processing. There's a compressor by default, and also send it to the peak meters. These are all in-process Jack clients, yes. Everything, even this USB gadget is the USB audio stuff. So there's two separate ones to make sure tricky to explain, but yes. So each individual client is the effect 1, effect 2, blah, blah, blah. There's a global mod host just to deal with MIDI CC input. This goes on the MIDI merger just to be able to listen to all the ports at the same time. It's easier to manage this through here, because then you can also change the mode of the MIDI. I can explain it a bit later if there's enough time. But basically, that gives you an overview of what's happening. Each plugin, each client, then a bunch of things behind the scenes just to deal with peak metering. Even on the Dwarf, there's now like a noise gate. So there will be something before, like after the system there's a little box here just to deal with the default noise gate processing. And then that is the one that connects to plugins. But yeah. Anyway, after this, then we have to deal with what we call HMI, human machine interface, which is what I describe as the top board. I don't have the unit open, so you cannot see it, but there is a board that is on the top of the unit, basically. That's why you call it the top board. That handles the knobs, handles buttons in directions. It has a little mini coprocessor in there. That part of the thing is of the product is not open exactly. All the things that I mentioned so far has been open except the ones I mentioned that is not. So there is one part that we, for business decisions again, kept as private, just so other units could not just replicate the thing directly. But the protocol that the system uses to talk to it is open. Sadly, it was not a thing in the beginning, which was very painful, especially because there was sometimes some little typos ruin everything, and it takes a while to actually find out. So always make sure you have some protocol running for these kind of things. One cool thing is that this HMI has direct system access. It's not like we have the serial lines going there, as I showed you on the bottom board. There's those pins that have serial lines. There's also a serial line that goes directly to the system. So I'm not sure if I can actually show it. Yeah, but I can. On the user's command, you see there's an HMI user in there, it's not us, it's something else. So the actual top board is listening to the output of the console. And whenever it detects that there's a login prompt, it logs into the system so they can do random operations. So there is the case of, for example, sometimes you change some parameters and you want to save the ALSA configuration, ALSA mixer values. If you want to reboot the unit, we did it initially before we had some other things in place. But it's just nice to have, if the unit needs to do something special, especially for the bootloader phase, I was hoping to get into a demo, but I don't think I can because it's a bit tricky. But if I put the unit, if I hold two buttons on the unit is going to interrupt the boot process, is going to run some custom commands, and that triggers a special, the special deploy mode. It's something that is not implemented by some kernel configuration, also bootloader configuration of pressing buttons, because these are not real buttons. They're a little bit different. But it's cool that we can basically simulate user input with this. The other thing to mention that then is also needed, because this is a device that has plugins. We wanted to sell plugins, so we had to deal with device authentication, as in each device talks to the cloud. We know where the device is. The end result is because we want to have commercial plugins, also for authenticating that units are valid, they're not just copycats. But the commercial vendors typically don't want to have something that is freely available to just copy. So we could do commercial, but still be open source completely, where we don't even do anything. You buy the plugin, you have the plugin, the binary, you copy it and whatever. But then we don't have any vendors talking to us anymore. So we had something in place that is some kind of DRM, but it's not quite DRM. Just to explain very quickly. So each unit has its own serial number, but that is fine. On the factory, every time the unit is made, we put we bump a number that's a serial number for the unit. Then we can identify where the unit is, all these other things. The special thing is the UID. So the bottom board has a special chip that is guaranteed to have a ID in there that is unique in the entire planet. Not unique within the system, as in software, but unique as in physical world unique. This is one way to know that for sure this device has this ID, and it can only work if it has this ID. We stored some GBG key in some EEPROM that the device has as well. This is used for saving data that is kept even after you delete all the flash. It's some kind of separate storage. It's very limited. It's only, I don't know if it's 1 kbyte even. I don't know. It's a couple of bytes that you can store in there. Then we built some LV2 API on top of this. This is like, it's a way to validate that the plugin is yours. It only runs on your unit, and there's no way to make it work anywhere else because it requires the actual unit. Robin here even helped creating this thing, which is quite nice. What is the time actually?
It's almost 6. So you're at a time.
Okay. Okay, I'll speed up through this very quickly then. We have a special mode. This is fancy enough that I think I should probably show it, because then the unit also needs some testing. What we did for this is to have a self-test mode, where when the unit is deployed within the factory, it boots up in a test environment, and it cannot work properly until that test passes. And because it's a bit weird on the interaction within the unit, now I need to connect to this thing again. I don't have time to show it, but basically we have a way for the unit to test itself, where you connect, because we have USB gadget, USB host, MIDI in, MIDI out, audio in, audio out. We just loop back everything. So the unit runs pretty much all the tests, software tests, and then there's some they have to press a button and this button verify that screens, LEDs, everything is fine. I thought I would have more time. Afterwards, there was optimizations, basically. I can describe that we have, the usual RQ tuning, but you pretty much do it on every single system. The jack with internal clients was intentional, just to get rid of the context switches. We also run jack in a special mode where we use private futexes, because everything is internal client. So I'm not sure it's exactly correct, but basically we reduce the time that the shared memory locks go into the kernel, because they don't have to. On the Dwarf, maybe it does not make a whole lot of difference, but on the first unit that was weaker, it made on a full, we added 8 more plugins on a full pedal board that we could use after the optimizations. We have a separate build root thing for dealing with the plugin dependencies. So that's, I think I have it, yeah. On the mod thing, we have the restore, the kernel, rootfs plugins dep. The kernel is separate because then it can be many for one single system. The thing is, the plugins dep, we basically build the libraries that the plugins use. They are not part of the main system, like FFT. We build it in a more aggressive way, basically, where we optimize it as much as possible, even more than the rootfs. We don't want to have fast math and other things on top of systemd. I wouldn't trust it. But for somebody that deals with audio, I don't know, it's quite fine. So there is an extra optimization just to get as much performance as possible. But then it's all, in the end, everything plugin step with the FS and kernel gets combined into one image. That is the system image. Yes. I'm out of time though, so let's say a lot of work in here, but then we get one device that is easy to deploy. I didn't even show it, but basically I'm pressing the 2 buttons. I boot it up while holding the 2 buttons. The unit now has blue LEDs, and instead of having a network gadget, it has the USB mass storage. I'll just show this to end. I don't actually, it needs a little bit of time, but then it appears in here. This is another thing just the kernel has, the mass storage device. the idea is then you copy a firmware file in here, you eject the thing. If I eject it, it's going to try to verify the thing that has nothing. So yeah, it turns red. It's starting to deploy. There's nothing, so it goes back again. The automatic updates, we have it through the cloud and other things that I don't have time to show, but this is one way to reinstall the software if you need. If you reinstall the software together with the data image, that means it does a full factory reset because it deletes the data partition. And yeah, super like optimized everything as much as possible because it's worthwhile and it's for one single unit. And yeah, thank you. And